Okay, let's start. Hello, everybody. A very good afternoon, everyone. So today we will be continuing our discussion, or we'll be solving problems on the same topic, that is the control system design in frequency domain. And we will be designing lead compensator and lag compensator using Bode plots. In the last week, we saw how to design these compensators using root locus. And now we'll be saying the same thing in frequency domain, right? So before we begin, let's revise gain margin and phase margin, gain crossover frequency and phase crossover frequency, so that it will be easier for you to understand the rest. So let's start. Let's start with gain crossover frequency. This we have learned when we were learning root locus as well, or Nyquist plot, polar plots. At that time, I also discussed this gain margin and phase margin in detail. So, but today we will also be discussing it. So, what is gain crossover frequency? So, it is the frequency at which the dB gain of the system becomes zero. So, or like here I'm saying gain in dBs, or if there is the actual value, then I can say that when the gain becomes 1, because when the gain is in dB, it's in log terms, so log of 1 becomes 0, right? I will explain this graphically using a Bode plot. So, for example, let's draw a Bode plot. So let's assume, so this is our omega, log of omega actually, and this is our 0 dB line, and this is dB. This dB is positive dB, and here negative dB. Right. So let's assume our Bode plot is something like this. Right. So let's assume our Bode plot is something like this. So this value of frequency is called gain crossover frequency. Why? Because at this point, at this value of frequency, my gain is becoming 0. So this is my omega GC, gain crossover frequency, right? So let me plot magnitude as well. This is again log of omega. And let's assume my magnitude is something like this, right? So then if I see this gain crossover frequency, this is somewhere here. So this is my gain crossover frequency, right? And this is -1. I hope you know this. I'm just revising. By the time others will also join, and then we can start with the design. So this is my magnitude plot, first one, and the lower one is the Bode phase plot. So this is phase. This is magnitude. So you can see at gain crossover frequency, this is my phase margin. So what is phase margin? So I'll tell you what is phase margin. We have discussed it in detail, but I'll again tell you it is the angle of GJ omega, HJ omega, or GJ omega at the gain crossover frequency plus 180 degree. Right? So we have learned this in detail. Or we can say this phase margin is, if this is phi, then it will be phi plus 180 degrees. So this is basically from the graph, we can see this point, that this area, this area is the phase margin, right? So, and when phase margin is above minus 180 degree line, then phase margin is positive. So this, if phase margin lies above 180, then it's positive. So this is positive phase margin. Right, so phase above minus 180 is considered positive, and phase below minus 180 is considered negative. So I hope this is clear. But now let's see this point. So this is the frequency where my phase becomes minus 180. So this is called phase crossover frequency, right? So my frequency at which the phase becomes minus 180 is called phase crossover frequency. And at this phase crossover frequency, what is the value of gain? So you see, my value of gain is something this. So this is my value of gain at phase crossover frequency. So this margin is called gain margin, right? Or we can write it like this: gain margin is equal to 20 log of magnitude of 1 by GJ omega. Wait, yeah, 1 by GJ omega at omega equal to omega phase crossover. And it's in dBs. Or if we solve it, 20 log of 1 will be 0. So it will be gain margin will be minus 20 log of GJ omega in decibels. Again, if my gain margin is below this 0 dB line, then gain margin is taken as positive. So this is positive gain margin. And if my gain margin is above this 0 dB line, then gain margin is taken as negative. Let me write this point. So phase margin or phase above minus 180 degree is considered as positive, while phase below, okay, below minus 180 degree is considered as negative. Similarly, if dB gain is above 0 dB, then gain margin is negative. And if dB gain is below 0 dB line, then gain margin is positive. So let me again recap. So basically, we will be now many people have joined. So basically, what we will be doing, we'll be designing lead compensators and lag compensators in frequency domain, right? So in frequency domain, we'll be using Bode plots to do the same, right? So I started this lecture with the revision of gain margin and phase margin. So when we learned this phase margin in our earlier lectures, I told you that two things are very important: phase crossover frequency and gain crossover frequency. Gain crossover frequency is the frequency where my magnitude becomes 1, or if it is in dBs, it becomes 0. So that frequency at which the dB gain of the system becomes 0 is called gain crossover frequency. And with this gain crossover frequency, we calculate the phase margin, right? How we calculate the phase margin? With this frequency, we calculate the angle of GJ omega, and after that, we add 180. That gives us the phase margin. And then my phase crossover frequency is the frequency when my phase becomes minus 180. And using phase crossover frequency, phase crossover frequency, we calculate gain margin uh, by taking the reciprocal of the magnitude, right? So now two things are there. Now I showed you this from the Bode plot. So again, let's assume this is my magnitude plot. So the frequency when my magnitude becomes 0 is called gain crossover frequency, and the frequency at which my phase becomes minus 180 is called phase crossover frequency. Then there are two regions. One region is for magnitude, one region is above 0 dB, and the other region is below 0 dB. Similarly, for phase, the region is above minus 180 degree, the other region is below minus 180. So in case of magnitude, if my dB gain, if it is below 0 dB line, then my gain margin is positive. And if it is above 0 dB line, then my gain margin is negative. Similarly, in case of my phase plot, if my phase, if it is below minus 180 degree, then it is considered as negative. If it is above minus 180 degree, then it's considered positive, right? See here, in this case, if my gain crossover frequency is less than my phase crossover frequency, we can see it here. The gain crossover frequency, it comes first, and then my phase crossover frequency comes. And here, so in the considered example, we have my omega GC is less than my omega PC. And also, I told you when gain margin, when dB gain is below, this dB gain, if it is below 0 dB line, then gain margin is positive. Here it is. So gain margin here is positive. Similarly, phase margin is also positive because it's above minus 180 degree. So we have this thing when omega GC is less than omega PC, and as well as what we have gain margin as well as phase margin positive. So in this case, if gain margin and phase margin both are positive, our system is stable, right? So you should know how we can judge whether my phase margin is positive or negative. And after that, what happens when my gain margin or phase margin, if they are negative, positive, or they are 0. So what happens to the stability? So if my gain margin as well as phase margin, if they are both positive, then my system is stable. If they are both negative, then my system becomes unstable. If they are 0, that is omega GC, phase crossover frequency becomes equal to the gain crossover frequency, and gain margin equal to phase margin equal to 0, then my system is marginally stable. So this was the case of stable system where my gain margin and phase margin both were positive, and my gain crossover was less than phase crossover frequency. Let's take another scenario where my gain margin um, gain margin and phase margin becomes negative, right? So yeah, let's take another example. So this is my omega. This is my 0 dB gain, right? So what's my gain margin is something like this magnitude plot is something like this, or even, yeah. And my phase, let's assume my phase plot looks something like this. Right, so this is minus 180 degree, this is 0 dB, this is negative dBs, this is positive dBs, right? So here, this is my gain crossover frequency, and this is my gain crossover frequency, and this is my phase margin. Similarly, this is my phase crossover frequency, and so this is my gain margin, right? So this was my phase crossover frequency. So in this case, what we have phase crossover frequency is less than gain crossover frequency, as well as we have gain margin is negative and phase margin is negative. So my system becomes unstable. So remember this, when your gain margin and phase margin both are negative, and that means your phase crossover frequency is less than your gain crossover frequency, and that means your system is unstable. Consider another scenario. Let me know if you have any doubt in between. So let's assume this is 0 dB. So let's assume I have something like this. So then this is minus 180. So this is my gain crossover frequency. This is my phase crossover frequency. This is phase positive, negative. So here we can say my gain crossover frequency is equal to phase crossover frequency. My gain crossover frequency is equal to phase crossover frequency, and gain margin is equal to phase margin is equal to 0. This means my system is marginally stable. Right. So yeah, the key takeaway is you should be able to identify when my gain margin is positive or negative, and you should be able to identify my gain crossover frequency and phase crossover frequency. That's it. So with that, we are good to go for the controller design. That's a compensator design in frequency domain. So anybody has any questions till now? Okay. So now let's start with lag compensator. We have studied this in previous lecture as well, so I'll not go into details of what lag compensator is, what does it do. We have already covered that, and I believe that you have gone through the lectures of the previous week as well. So you have better understanding of what the lag compensator does. We basically will focus on the controller design and how you'll be able to solve your assignments, right? So again, for the sake of completeness, so let's assume this is the transfer function of my lag compensator. Right, so my beta is greater than 0. In case of a lag compensator, my pole is closer to origin, right? So if this is my pole 0 plot, then my pole is closer to origin. Okay, so or we can write it like this. This GC of S, it can be written as K into 1 plus ST divided by 1 plus S beta T. Okay, where this K is equal to Kc into beta. So I did nothing. I just replaced Kc beta with K, which is actually the DC gain of the compensator. Now, you should understand this thing that whenever we are studying these compensators, lead compensator or lag compensator, they're always connected in series with the system. For example, if you have a system GS, then you will add a lag compensator like this. So this will be GC of S, right? So then this will be my output, unity feedback if I assume. So it will be like this, right? So if it is unity feedback, then -1 here. So the scenario will always be like this. So in this case, what will be my OLTF, open loop transfer function? That will be this GC into GS because these are in cascade, right? So what will be OLTF in this case? OLTF will be GC of S into G of S. So whenever I write OLTF, I may not draw this diagram. You have to keep this diagram in your mind, because the controller or the compensator, that has to be connected like this, always in cascade with the system. So this is my OLTF, open loop transfer function, and what it is GC of S we have calculated, and GS it's given. So it will be K into GS into 1 plus S tau, ST into 1 plus S beta T. So what I did, I wrote this thing, I wrote this K here, then I wrote this GS, then I wrote the other part of the compensator transfer function, right? And we call this part as G1 of S. We call this part as G1 of S, that will be equal to K G of S. I'm basically explaining you the steps of controller design, like how we need to tackle these problems of lag and lead compensator in frequency domain. So first of all, what we will do, we'll be given a system and we will take an open loop transfer function. So this will be our step 1. So we will take OLTF, open loop transfer function, and then write that in this fashion. Then denoting K into G of S by G1 of S, and this we call as uncompensated system. Uncompensated system. This one is from the compensator, so this will be called as the compensated part. So this will be from the compensator. So first step is to write OLTF, and then from OLTF obtain G1 of S, which is KG of S. Then the next part is, the next part of this step is to find the value of this K. We know, like we have been solving this problem from last 2 weeks. So we know the value of this K is found by from the given specifications. We'll be given that, okay, velocity error constant will be this, and then using that, we can find the value of k. If it is a first order system or a second order system, we know how to proceed. So then what we do, we find the value of k from the specifications, from the given specifications, from the given specs. Okay, so this completes my step number 1. Now step number 2. So in my step 1, what we did, just find the OLTF, get G1 of S, which is the uncompensated part, and find the value of K from the given specs. Now, step 2 is we need to sketch the body plot of G1 of S. Sketch body plot of G1 of S. So if you have gone through your assignment, the first line that's written there on the top is you can use MATLAB for solving these assignments, because that will make this relatively easier. Otherwise, it will take a lot of time, because you'll be drawing body plots, then saying gain crossover frequency and phase crossover frequency, calculating gain margin. It will take a lot of time. That's why you're allowed to use MATLAB in order to solve the assignment problems, right? But yeah, again, for that, you would still need to know the procedure. Okay. So the second step is you need to sketch the body plot of G1 of S, which is the uncompensated system. And by utilizing the value of gain K, which is calculated in step number 1. So I'll write it complete using the value of K calculated in step 1. Okay. So when we sketch this body plot, then we can obtain, we will know the gain margin, phase margin, gain crossover frequency, phase crossover frequency of this G1 of S. Then obtain phase margin and phase crossover frequency of G1 of S. This completes our second step, right? So in second step, we'll just make the body plot and obtain phase margin and phase crossover frequency. Now step 3. So in step 3, what we'll do, you will make use of the specification that are given. So in your questions, you'll be given that, okay, you need to design a compensator such that my phase margin is this, my velocity error constant is this, etc. So usually phase margin is specified. So, and let that phase margin, let phi s be the specified phase margin. Right? And then you will be asked, okay, this is your specified phase margin of the system. You need to design a compensator such that your phase margin becomes this, right? So then you need to find the required phase margin, which I'm representing as phi r. So you are given a phase margin, which is your specified phase margin, which is phi s. And then you're asked to find the required phase margin. So yeah, let me write it complete. Required phase margin, that will be phi r. Okay, so this phi r, it is given by phi r is equal to phi s plus some epsilon, which is the error. This epsilon, where this epsilon is to compensate the phase lag introduced by the lag compensator. In your assignment problems, you're specified that you need to take epsilon equal to 0, because you're solving this multiple choice questions. So you need to have unique answers. But in general, these design problems, they can vary. So it depends on like what you want to achieve, how good your response should be. So this normally the value of this epsilon is taken as 5 degree to 12 degree. So these things will be more clear when we solve the problems. So then in step 4, what you are going to do, you're going to find the required phase margin, right? And wait, yes. So now then step 4, in step 4, what you do, corresponding to the required phase margin, so corresponding to the required phase margin by R, we determine the frequency omega R. So what will happen? Now my phase margin will change because I'm being specified some phase margin. Now my phase margin will change. And when my phase margin changes, then my phase crossover frequency will also change because I get my, my gain crossover frequency will also change because I get my phase margin corresponding to gain crossover frequency. If I'm asked, okay, now this should be your new gain phase margin, it means my gain margin will change. So with that, with corresponding to the new phase margin, I will determine the new gain crossover frequency, which is called omega R here. So this is the required omega R, or in better right, that is the frequency at which the phase angle of the OLTF is minus 180 plus pi r, right? So it's pi r is now the required phase margin, right? So this is actually the new gain crossover frequency. So this is new gain crossover frequency. So when we find the required phase margin in step 3, then corresponding to that in step 4, we'll find the new gain crossover frequency, correct? And what we will do in step 5, then what happens? When we find the new gain crossover frequency, we have new phase margin, and corresponding to that, we have uh, uh, like this gain crossover frequency means our magnitude should be 0, right? Because gain crossover frequency is that value of frequency where my magnitude becomes 0. But my magnitude will not be 0 initially because now I am compensating the system. So there will be some value, and I need to make that 0, right? This will be more clear when we do the example. Just for the sake of just bear with me for some minutes. Then this will be more clear when we solve the example. So what I am saying, we need to determine the attenuation necessary to bring the magnitude curve down or up to 0 dB, because we want, because then and only that can be gain crossover frequency uh, at the new gain crossover frequency. And this attenuation is given by, this attenuation is minus 20 log of beta, or 20 log of 1 over beta, right? The value of that attenuation, we'll get some value from the Bode plot, and that corresponds to 20 log of 1 over beta, and therefore we will get the value of beta. So what we will get? We'll get determine beta. So basically what we are doing, we are designing a lag compensator. So what is lag compensator? We need to design this Kc, we need to design beta, this T, and that's it, right? So beta, Kc, and T. We need to design these values. We need to design these in such a way so that my requirements are met, whatever I'm given. So this procedure I'm doing to find the values of beta, Kc, and T, right? So now I'll determine the value of beta. And I told you that I need to attenuate the magnitude. I either have to bring that down or I either need to bring that up so that that becomes 0 dB. So if I need to downshift that, if I need to downshift, that should be taken as negative. If I need to upshift the magnitude curve, that needs to be taken as positive. This is just the procedure. So we found beta. Then using beta, we can find K because K is equal to Kc into beta. So from here, we know K, we have calculated K from step 1, we have calculated beta, so we can find Kc. It implies Kc is K over beta. So we have calculated beta, we have calculated Kc, so we now need to calculate T, right? So what is T? So T is the corner frequency, that is 1 over T, which it is taken as omega R, which we calculated as new gain crossover frequency by 10, right? So this 1 by T, which is the upper corner frequency, it's taken as omega R over 10. So then we can easily determine T. From here, we can determine T. So we have then when we have determined T, we can compute the lower frequency due to pole, which will be 1 over beta T. So our job is done. So we have calculated beta, we have calculated Kc, we have calculated T. So we have now somehow got the parameters of the lag compensator. So what is our last step? Step 7. Step 7 is to sketch the Bode plot. Sketch the Bode plot of the like compensated system, the whole system. That will be my GC of S into G of S, and then verify the design. So then we need to verify, okay, I needed phase margin to be this. Am I achieving that? So yeah, this is my last step. I need to draw the Bode plot and confirm the design. So now let's verify this. Let's do this using an example. It will be more clear now. Let's assume we have an open loop transfer function, or we have a system GS is given by 0.035 divided by S into 0.5 into S into 1 plus 0.04 into S. Okay, so we are given this system, G of S, and the question is design a lag compensator to give velocity error constant Kv equal to 27.3 per second and phase margin of 45 degrees. Right, so as soon as this lecture ends, you'll do one thing. Whatever we will do today, you'll just verify this from MATLAB. So from MATLAB, you'll plot this transfer function and see what's the Bode plot. like what is the phase margin, gain margin, and then uh, uh, what is the compensation that is needed in order for us to get this phase margin of 45 degrees. Okay, so for the time being, let's solve this. So what is our step number one? Our step number one is to find the uncompensated system G1 of S, which is equal to K into G of S, right? So this is our step number one. We need to find G1 of S, which is equal to K into G of S. So what will it be? So it implies my G1 of S is 0.035 into K divided by S into 1 plus 0.5 S, 1 plus 0.04 S. Right? So this is my G1 of S, and now I need to find the value of the gain K from the given velocity error constant. Okay, so my KV is given. So what is KV? KV is limiting S tends to 0, S into G1 of S. It's equal to limiting S tends to 0, S into 0.035 into K divided by S into 1 plus 0.5 S into 1 plus 0.04 S. This S and S will go. You will finally get KV is equal to 0.035 K. But KV is given as 27.3. Just from the question. KV is given as 27.3. It means it implies my K is equal to 780. Okay, so when my K is equal to 780, it implies my G1 of S is equal to 27.3 divided by S into 1 plus 0.5 S into 1 plus 0.04 S. So basically what we have done, we have found our uncompensated system, that is G1 of S. So anybody has any doubt until here? Now let's move to step number 2. So step number 2 is sketch. Sketch the Bode plot. Sketch Bode plot of G1 of S. So in your assignment problems, you'll not solve this Bode plot by hand or like manually. You just need to draw this in MATLAB, right? It's allowed. So let's draw the Bode plot. So that this is 0 dB. So Bode plot will be something like this. Okay, so this is 50. This is in dBs, 50 dB, right? And let me draw the magnitude plot as well. So this is the Bode plot that you will have to draw with MATLAB. So I'm getting something like this. This is omega. I did not write it again and again. Right. So from this Bode plot, what do you identify? You'll identify that this is your gain crossover frequency. And this is your phase crossover frequency. right? From this gain crossover frequency, this is your gain crossover frequency. It means this is your phase margin. And this is your phase crossover frequency, and this is your gain margin. Okay, is this clear? So this is your, so I identified my phase crossover frequency, gain crossover frequency, my gain margin, and phase margin. So I can see my phase margin is, it's negative. Of course, I know that it's below minus 180 degrees. And how much is it? Minus 0.166 degrees. So it's negative. And my gain margin is, it's also negative. It's 0.0, not right. My gain margin is minus 0.096 dBs, right? So gain margin is negative. My phase margin is negative. My omega BC is less than my omega GC. My gain margin and phase margin both are negative. It means my system is unstable. Right? So my system is unstable. Now I'm asked in the question, so design a lag compensator such that my phase margin is 45 degree, and 45 degree is a positive number. It means I will also be stabilizing this system, right? So this system is unstable. So I need to design a lag compensator such that my phase margin becomes 45 degrees. That is, it becomes positive. So it means I am also stabilizing the this system, as well as I'm achieving the desired performance specifications. Okay, this omega GC, the value of omega GC here, you'll find from the MATLAB, it will be 7.11 radians per second, and omega PC will be 7.07, slightly less than, but yeah, still less than omega GC, right? So this was our step number 2. So we needed to sketch the gain margin and phase margin. The magnitude and the phase plot, and find the gain margin and the phase margin. So now what will be our next step? We will design a lag compensator so that will make the system stable and also provide, and so when it makes system stable, it provides the required positive phase margin. So my step 3 is, to look at the specifications that are given. So it's given that my phase margin that the specified is 45 degree, right? So it's specified as 45 degree, and I said my required phase margin, it should be phi s plus epsilon. And why I'm adding this epsilon, you should go through the lectures there. It's explained in detail, because if you see the polar plot of the lag compensator, it increases the value of gain crossover frequency. So there's a lot of, like, it will take a lot of time to explain. So you just go through the lecture series or this NPTEL lectures. So there it's explained in details. For the time being, you just remember. So this required phase margin is phi s plus epsilon. And let me take epsilon as 5 degrees. So my phi r will be 45 degrees plus 5 degrees, which is equal to 50 degrees. In your assignments, you need to take this epsilon as 0. Just take phi s equal to phi r, because again, you're solving multiple choice questions, you need to get unique answers. So this was my step 3. I need to find this phi r, that is.
Sorry, epsilon you have taken arbitrarily.
Yes. So I told this epsilon should be between 5 to 12 degrees. In your case, it should be 0 degree. Don't take it. It will be specified. But yeah, for the sake of design and the completeness, tomorrow you'll be designing this for some other problem. So you need to know this. And why this is why we are taking this, there are reasons. Okay.
Yes, sir. Okay.
So now my phase margin should be 50 degrees. So if I go back, to my 4D plot, where should this 50-degree phase, where should this 50-degree phase margin be? So from this point, this omega PC, to the right of omega PC, I have negative phase margin. It means it is somewhere here to the left of omega PC, right? So you'll identify, because obviously you have this plot from the MATLAB. So you identify, let's assume you have it, you have this region, which gives me the phase margin of 50. Let's assume this is that region which gives you phase margin of 50. So it means the gain crossover frequency. So phase margin is always calculated at gain crossover frequency. So this is my 50. So here, my phase margin should be 50. It means my new gain crossover frequency should be somewhere here. But the value of magnitude is not 0 here. The value of magnitude is something else, right? So here the value of magnitude is not 0. It is 23.3. So, but it should be 0. Why? Because when I calculate phase margin, that is calculated at gain crossover frequency, and at gain crossover frequency, my magnitude is 0. Yes, please. Okay, let me see, Tim. Okay, so my magnitude is not 0. So I need to make this magnitude 0. So it's 23.3. I need to make it 0, right? So now I am downshifting it. I'm not upshifting it. I told you when I'm doing the downshifting, I need to take the value as negative, right? Wait. So my step number 4 is to identify this new gain crossover frequency, which I will call it as omega r, right? So this new gain crossover frequency, the frequency which 50-degree phase occurs from Bode plot, right? So you have this Bode plot, you have generated this from MATLAB, so you have all the details available. So from this Bode plot, you will go and see when this 50-degree phase margin occurs at that frequency. What will that frequency be? That is my omega r, that is my new gain crossover frequency. And that you will see from the Bode plot, it will be 1.48 radians per second. So this is my new gain crossover frequency. When it is gain crossover frequency, it means the value of gain should be 0, but value of gain is not 0. Value of gain is 23.3 dBs. It means I have to take the magnitude, I have to attenuate the magnitude from 23.3 dBs to 0 dBs. Then I can achieve the required stuff, right? So I'll write here, it is necessary to bring the magnitude curve down by 23.3 dBs. Why 23.3 dBs? Because at this value of omega r, at the new gain crossover frequency, the value of magnitude comes out to be 23.3 dBs. So that's why this 23.3 dBs. So it means from the steps I told you, it should be minus 20 log of beta is equal to 23.3 dBs. Since it's downshifting, I'll take a negative. It implies my log of beta is equal to 23.3 over 20, or my beta is equal to 14.62. So I have calculated beta. Again, I told you, so this omega, now I need to calculate T, right? So this omega CZ, that's the upper corner frequency, that is given as omega R over 10, which is equal to omega R is 1.48 divided by 10, which is equal to 0.48 radians per second. Now I know this omega CZ, the upper corner frequency, it is 1 over T. It is given as, so 1 over T is given as 0.48, right? So it means, it implies my T is equal to 6.75. So I calculated T. I can also calculate beta 1 over beta T. That is equal to 14.662 into 6.75. It's equal to 0.0101 radians per second. These are actually not needed, but yeah, just calculating it. So what is my lag compensator? My lag compensator, GC of S, will be, it is 1 plus ST divided by 1 plus S beta T. So this will be equal to 1 plus 6.75 into S divided by 1 plus 98.68 S. So this is my lag compensator, which I calculated. Okay, so I calculated the parameters later. What I need to do, I need to find the Bode plot. So what I'll do now, this GC of S into G of S. So when you do this, what you will get, 27.3 into 1 plus 6.75 into S divided by S into 1 plus 98.68 S into S, sorry, into 1 plus 0.04 S into 1 plus 0.5 S. So this is your compensated system. This GCS into G of S, this is your compensated system. And what is your final step? Your final step is to sketch the Bode plot of this system. So when you sketch the Bode plot of this system from MATLAB, when you sketch the Bode plot, what you will get? Do this. This is your homework. Do this. When you sketch it, you'll find the gain crossover frequency to be 1.5 radians per second, the phase crossover frequency to be 6.8 radians per second, the phase margin to be 44.5 degrees, and gain margin 22.5 dBs. So this was the required, this 44.5 degrees, this was the required phase margin. So I'm achieving it. So yeah, that's it. So this is how I calculated this. This is how I designed this Bode plot. But remember one thing, I took epsilon equal to 5 degrees here. So if you had not taken epsilon equal to 5 degrees, you would have obtained a lot of error, right? So, but again, that's fine in your case because it's being asked in your questions. Take epsilon equal to 0. So that's why this epsilon is important. So it's because of this epsilon I could achieve my gain margin, my phase margin close to what was desired. So anybody has any questions until here? Because if you understood this, in the same way, we will design lead compensator. The steps are almost the same.
Sir,
Anybody? Yeah.
sir, what is that? Omega R by 10?
Okay. Yeah, it's actually the design part. So this one. So,
Yes, sir.
okay, wait. I'll show you. So basically, we're designing a lead compensator. Okay. Sorry, a lag compensator. And a lag compensator has a zero and a pole. Correct? So a lag compensator has a zero and a pole. So one pole occurs at, so the pole occurs at 1 over minus 1 over beta t, and the zero occurs at 1 over t. And beta is greater than zero. And in case of a lag compensator, this beta lies closer to origin. It means, so if you write this in this way, wait. So you have two corner frequencies here. Where was I? Omega R reversing. Yeah. So you have two corner frequencies here. This omega z CZ is corner frequency because of zero, and this is omega C P because of corner frequency because of pole, right? And omega CZ, this is 1 over T, and it's taken as omega R over 10, where omega R is my new gain crossover frequency. It's in the design. It's taken as omega R over 10, right? So the corner frequency, because of zero, is taken as omega R over 10, which is equal to 1 by T. Some people also take it omega R over 2. So it will be specified. Again, it's a design problem. So you can come up with n answers. Doesn't matter. Okay.
Okay, sir.
Okay. Anybody else?
Sir, what is the correct format for lag compensator or lead compensator? Sir, sometimes they use 1 plus AT by 1 plus T, 1 plus ATS by 1 plus TS.
Forms are the same. So it depends. So in like, for example, you have seen this form as well. 1 plus S over tau or divided by 1 or S or beta tau. This form, and here is some K. So if you see this form, which we have taken, I'll show you it. So for example, this form, GC of S, let's assume I'm taking of a lead compensator, let's assume, or they are the same, just the value of beta matters for alpha. Here I'm taking as alpha, 1 plus alpha t. So this is one form, right?
So,
If you take alpha common, what will happen? So if you take alpha common, so it is KC alpha. Sorry, if you take t common from the numerator, so if you take t common from the numerator, it will be S plus 1 over t. And you take alpha common from the denominator, it will be alpha and t, sorry, alpha t S plus 1 over alpha t. This, this alpha t and alpha t goes, so it is Kc into S plus 1 over t divided by S plus 1 over alpha t. Again, the same form, right? So it's
yes, sir.
basically the same. It's basically the same form. Any other confusion? So should we go to the design of lead compensator? Okay, let me first just again revise the design of lag compensator. So you will be given a transfer function, g of s, and you will be asked, okay, yeah, anybody has any questions? Somebody is unmuted. Okay, so you'll be given a transfer function, g of s, and you'll be asked, okay, design a compensator for the system such that my velocity error or any error is this much and my phase margin is this much. So what you'll do, your first step is to find the uncompensated system, which is equal to k into g of s. And then k you will find from the specifications of kv or ka, whatever is given. Right, so once you get this g1 of s, then you will draw the Bode plot of this system and find, okay, what is the value of gain margin and phase margin and how much I need to compensate. Right, so you'll get an idea and you'll know whether my system is stable or unstable based on that Bode plot. Correct. So then after this Bode plot, you will see what are the specifications. What are the specifications that are given? So for example, in this case, it was given that my phase margin should be 45 degrees, but initially my system was unstable because my phase margin was negative. Now it is being asked in the question that the phase margin should be 45 degrees. It means I should be able to stabilize the system as well as achieve the phase margin of 45 degrees. Right? And then, okay, based on some design stuff, I'm adding some error, which is because of the lag compensator. So 5 to 12 degrees. So I added 5 degrees here. So that was my required phase margin became 50 degrees. That's it. And after this, I need to locate this phase margin on the magnitude plot. So where this phase margin occurs. And based on that phase margin, I'll get the gain crossover frequency, which I'm naming as omega r, which is my required gain crossover frequency or my new gain crossover frequency. So with this omega r, my magnitude has to be 0. So my magnitude should be 0 because it's a gain crossover frequency, but my magnitude will not be 0. I need to attenuate that. I need to either take that up or take that down. So it depends. If I'm taking that down, I should take minus sign. If I'm taking that up, I should take positive sign. And that shifting will give me beta. From this 20 log of beta, I'll get beta. So once I get beta, I should know I should get the upper corner frequency. The corner frequency because of 0, that is omega r over 10 or omega r over 2, whatever it is. So I'll find t, and when I find t, then I can directly write the lag compensator transfer function. And after that, I just find the overall OLTF because of this lag compensator, which is calculated here. And then you calculate, you draw the Bode plot, you'll see, okay, whether my specifications are met or not, right? So then you will see, okay, yes, if you have designed it correctly, then yeah, your specifications will be met. Now again, let's go to lead compensator design. So my lead compensator transfer function that is given. Okay, here in the case of a lag compensator, I was using beta, and now here I will use alpha to differentiate. So my lag compensator transfer function will be 1 Kc over alpha 1 over Ts divided by 1 plus alpha Ts. Again, same. But yeah, if I take common t from the numerator and alpha t from the denominator, what I'll get this Kc into s plus 1 over t divided by s plus 1 divided by alpha t, where my alpha is less than 1. Right? So if I draw the pole zero plot of my lag compensator, we have learned this in detail in the last week. My zero will be near to origin and my pole will be further away from the origin. Right? So we have learned this detail, why my zero is closer to origin and why there should be some distance. In case of a lag compensator, there should not be much But yeah. So this is my pole zero location of a lag compensator. Now, one important thing to notice here is that in case of a lead compensator, you will be asked to find in some numericals, to find the frequency which maximizes the phase, right? So frequency which maximizes the phase by can be written as, remember this is very important formula. So the frequency omega m, which maximizes my phase, is given by 1 over t into alpha. Okay, or it's actually the geometric mean. It is the geometric mean of two corner frequencies. That is, omega m is the geometric mean of two corner frequencies. My one frequency is 1 over t. My other frequency is 1 over alpha t. That's how, if I take it t square, it will be t outside and it will be the root alpha. So it's actually my geometric mean of two corner frequencies. You can directly find this from the corner frequencies. So this is my frequency which maximizes the phase, and the maximum phase phi m is given by, let me write it here only. So my maximum phase phi m is given by sine inverse of 1 minus alpha divided by 1 plus alpha. Alpha, from here, right? So my phi m is, this is the maximum phase. So the frequency which maximizes the phase is given by the geometric mean of the two corner frequencies. That maximum phase is given as sine inverse. It's actually derived in detail in your lectures. Now let's move towards the design part. Again, we'll move step by step. I'll first explain the steps, and then we'll solve a problem to explain the steps. So what was my step 1 in lag compensator design? The same is that in case of a lead compensator design. My first step is, okay, for the sake of completeness, I'm writing, so g of s is my lead compensator transfer function. It will be k into 1 plus ts divided by 1 plus alpha ts, where my k is kc into alpha. Okay, then what will we do? We'll find OLTF. Okay, my OLTF will be GC of S into G of S, which will be written as 1 plus TS divided by 1 plus alpha TS into G1 of S. Again, the same way I wrote in case of a lag compensator, where G1 of S is equal to Kg of S. So this is my uncompensated system. This is my compensated system. Right, so this is my step 1. Okay, yeah, this one more part of the step 1 is we need to determine the value of k. Determine the value of k, satisfying the requirements, because that will be given in the question. So my step 1 is same as that of lag compensator, as well as my step number 2. So my step number 2 is, from using gain k, Draw the Bode plot. Draw the Bode plot of G1 of S and determine the phase margin of the uncompensated system. That will give us an idea, okay, how much lead angle, how much angle we need to compensate, we need to provide. Uncompensated system. And what will be my step 3? My step 3 is determine, okay, again, like from this step 2, we should be able to determine the necessary phase lead to be added in the system. So my phi r, that is the required phi r, let's assume it is the phase margin, which is given, or let's, okay, it was phi s. So phi s is the phase margin, which is given, and phi is the phase margin calculated in step 2. Then phi m, which we need to calculate, maximum phase will be phi s minus phi, right? So plus some error, again, epsilon, I told you, 5 degrees to 12 degrees, we will take. In your case, you'll take it 0. So you'll calculate this phi m here. It will be the maximum phase, right? So you'll add an additional 5 to 12 degrees to the phase lead angle, again, because the addition of the lead compensator, that shifts the gain crossover frequency to the right and decreases the phase margin. So in order to compensate for that, we take this additional 5 to 12 degrees. Again, you go to your lectures, you'll get details on it. So from this, you'll calculate this phi m. Then let's go to step number 4. My step number 4 is determine alpha using sine of phi m is equal to 1 minus alpha divided by 1 plus alpha. This formula, this is coming from this formula. So from this formula, you know phi m, so you'll calculate alpha, right? So then in step 5, now in step 5, you will determine, wait. So in step 5, you will determine the omega m. So corresponding to this phi m, you need to determine this omega m, where the, and how you find this omega m, right? So this determines, so okay, so first you find this phi m, and based on this phi m, you find alpha, and there will be a corresponding omega m. So maximum phase will occur at some frequency omega m that you will determine, that will be determined. So determine this omega m where the magnitude, there is a derivation of all these. I'm just writing the steps. Where the magnitude of the uncompensated system, where the magnitude of the uncompensated system G1 of S is equal to 10 log of alpha. Okay, so this will be my new gain crossover frequency, right? So this will be by my new gain crossover frequency. So I also know this omega m is equal to 1 over alpha into root t. So from here, I know omega m, I know alpha, I can find t. So then, sorry, I wrote this wrong. So this is 1 over t into root alpha. So I know alpha, I know omega m. I should be able to find 1 over t. So we will determine 1 over t. So I got t, I got alpha. So what is left? My kc is left, right? So my lead compensator 0. Let's call this as step 6. This is not required because we are already done, just for the sake of completeness. So corner frequencies, my 0 is at omega is equal to 1 over t. So I know 1 over t, I know t, I know 1 over t. My pole is at omega equal to 1 over alpha t. I know alpha, I know t. So in step 7, I will find the value of Kc as K over alpha. So this we can find earlier as well, but yeah, again. So I'll find Kc. Then in step 8, I'll sketch the Bode plot to verify the design. Correct? This is a bit more easier, right? So let's verify this using an example. That will be, then it will be more clear. Let's assume my g of s is 12 into s plus 2. Okay, my g of s is 12 divided by s into s plus 2. And my question is, design a lead compensator such that the system satisfies the following. kV is 24 second inverse. Phase margin is 55 degrees. Gain margin is greater or equal to 13 dBs. Okay. So if you see this system, what is the order of this system? What is the order of the system? G of s. Anyone?
2, sir.
Yeah, it's a second order system. And can you tell me what is the what so based on this, what will be the gain margin? You know the second order system, the gain margin is? Gain margin is infinity in case of a second order system. So that's not a problem for us. So, but yeah, we need to make sure my phase margin is 55 degrees. So again, it's a second order system. It will always be stable, right? So let's solve this problem. My first step, okay, my step 1 is to find G1 of S, which is equal to K into GS, right? And it implies my G1 of S is equal to 12K divided by S into S plus 2, where this K is Kc into alpha. Okay. Now we need to find the value of K from the specifications. We are given as Kv is equal to how much? 24. But this Kv is equal to limiting S tends to 0, S into OLTF. Correct? So if we calculate this, it will be limiting S tends to 0, S into 12K divided by S into S plus 2. I wrote it directly because I assume that you now know this in a better way. We have done so many problems. So it means KV is equal to 6K. It implies my K is equal to 4. Right, so my K is 4. It means my G1 of S is equal to 12 into 4. So it will be 48 into S plus 2. Right, so this will be my G1 of S, which is my uncompensated system, but it's of second order. Right, so since this is a second order system, my next step is step 2. My next step is to draw the Bode plot. So again, use MATLAB and draw the Bode plot. But since this is a second order system, for second order system, things are quite standard. You have formulas for these second order systems, right? So we can use MATLAB to draw the Bode plot, but we can also use formulas to directly calculate gain crossover frequency, and from that we can calculate the phase margin. Right, so there are formulas for the second order system. So if we see this is I can write it like this. It is 48 into S plus 2. So the general form, I can write it like this: 48 divided by S square plus 2S. So here my omega, if I compare it, my omega n will be under root 48, and my zeta will be 0.144. Right, so how this is coming, 2 omega zeta n is equal to 2, and from there it will come. It's very, very easy. So I directly wrote omega n will be 48 and my zeta is 0.144. Now what is my gain crossover frequency? My gain crossover frequency is given by omega gc is omega n under root of minus 2 zeta square plus 4 zeta 4 plus 1. Again, why I am doing this, why I am writing formulas for this, because this is a second order system. You should know an alternative approach as well. Tomorrow, if you're writing an exam where this question is asked, you don't have access to MATLAB, so you might opt to this method. But again, you can do this using MATLAB as well. So this is my gain crossover frequency. By simplifying it, you will get my omega GC as 6.786 radians per second. We found out the gain crossover frequency. Similarly, my phase margin will be tan inverse 2 zeta under root of minus 2 zeta square plus under root of 4 zeta 4 plus 1. So when you calculate this, it will be phi is equal to phase margin is equal to 16.3852, right? And what will be my gain margin? My gain margin will be infinity because it's a second order system. So this was directly from the formulas, but we can again draw it from the Bode plot. So let me draw a Bode plot also. Let me draw a Bode plot. Okay, so this is my 0 dB. This is my minus 180 degrees. So if I draw the Bode plot, it will be something like this. Right. So this is my Bode plot. This is my gain crossover frequency. So this is my phase margin. Right. So this is my phase margin. What is phase margin? 16.39 degrees. It's positive. Then what is my what is my phase crossover frequency? Can anybody tell me what's my phase? What is my phase crossover frequency? My phase crossover frequency is infinity, right? So it will go to infinity, and at infinity it will cross this minus 180 degree, and accordingly I will have this phase margin as infinity. Right, so this was from the Bode plot, the same thing. So we got this gain crossover frequency and phase crossover gain crossover frequency, phase crossover frequency, and the gain margin and the phase margin. So gain margin is positive. Gain margin is infinity and phase margin is positive. It means the system is stable. Now from this 16.39, we need to obtain in step 3. So my step 3 is phi s specified is I should get 55 degrees, right? So this is my required phase this is my specified phase margin, which should be 55, and I know my phi m will be phi s, that is 55 degrees, minus phi calculated in step 2, that is 16.39, plus epsilon, right? And epsilon again I'm taking is 5 degrees. So my phi m will be 43.6 degrees, right? So my phi m will be 43.6 degrees. So corresponding to this phi m in step 4, corresponding to this phi m, I should calculate alpha. So I know this sine of phi m is equal to 1 minus alpha divided by 1 plus alpha. It implies, if you solve it, phi m is 43.6. You put in the values, you get alpha equal to 0.1837. Right? So now, what I told you in the other step, when we calculate this alpha, then we need to determine this omega m, where the magnitude of the uncompensated system is equal to 10 log of alpha, right? So what we will find, we'll find 10 log of alpha. So what is step 5? I'll find 10 log of alpha, which is equal to 10 log of 0.1837, which is equal to minus 7.36 dBs. So I got the magnitude 7.36 dB. So the value of magnitude when it is 7.3, the frequency of the frequency at which this magnitude becomes minus 7.36 gives me omega m, right? So if we go here, so I need to find my this magnitude. So let's assume it becomes let's assume it becomes So let's assume this point is minus 7.36 dBs, right? So then this frequency is omega m, right? So from the Bode plot, you should be able to identify, you should be able to calculate this omega m as 10.6 radians per second. You just need to do nothing. You have already plotted this Bode plot from the MATLAB. Just locate this point where my magnitude is minus 7.36 dBs. The value of frequency at that magnitude is called as omega m. So you got omega m, 10.6 radians. But you know this omega m is equal to 1 over t into under root of alpha. You know now alpha, you know omega m. Can you calculate t? Yes. So it implies my 1 over t will be equal to omega m into root of alpha. It will be omega m is 10.6 radians per second. Alpha is 0.1837. So my 1 over t will be equal to 4.497. Okay, in my next step, that is step 6. What is my 0? My 0 is 1 over t, which is given by omega at 1 equal to t, which is given by 4.497 radians per second. What is my pole? My pole is at omega 1 over alpha t, which is 4.497 divided by 0.1837, which is equal to 24.98 radians per second. In my step 7, I need to find Kc, which is equal to K over alpha. Implies my Kc is, my K is 4, my alpha is 0.1837. It implies my Kc is 22.22. So I'm done. I found Kc, I found alpha, I found t. So I can write the transfer function of the lead compensator. So it will be Gc of s is equal to Kc alpha 1 plus Ts divided by 1 plus alpha Ts, which is equal to Gc of s 3.99 into 1 plus 0.2224s divided by 1 plus 0.0400s. So then the transfer function of the whole transfer function of the compensated system becomes Gc of s into G of s, right? So you'll just put in the values. Then in MATLAB, when you draw the Bode plot, what you will get, your gain crossover frequency is 10.5 radians per second. Your phase margin is 54.8 degrees, roughly 55 degrees, and your gain margin is infinite. We can see all the specifications are met. That's it. So we are done with the compensator design. Is it understood? Should I revise? Have you understood this? Anybody has any questions? So the good thing is you have to do MATLAB. You have to do this, you have to plot this, you have to draw these Bode plots using MATLAB. So that's the easier part. And it's clearly fine because you're allowed to do that in order to solve your assignment. There are other ways also to solve this gain crossover frequency or to find gain margin and phase margin, which I am directly taking from the Bode plot. You can just calculate it. For example, if you want to calculate phase margin, you need to calculate gain crossover frequency. So you'll find gain crossover frequency, and that is the frequency where my magnitude is 1 or my dB gain is 0. So you'll put dB gain 0, find the magnitude, get the value of omega GC in terms of like as it is, you'll find the value of omega GC, then find the angle with that omega, then add 180, so you'll get phase margin. But since it's allowed, since it's directly given, it's written there in your instructions that you can use MATLAB. No need to calculate, just directly write from the body plot. You can use this command margin of, for example, G. So this will give you phase margin, gain crossover frequency, phase crossover frequency directly from the MATLAB. Right? So any questions, or otherwise we will end this lecture here.
For third order system, what is the how to proceed, sir? Third order system. Third order system.
Third order system. For third order system, first step exactly the same. Okay.
Yes,
No
sir.
problem in the step. Second step, what you will do, you cannot calculate. There are no well-defined formulas. Directly draw the Bode plot from the MATLAB.
Okay. Okay. Then we have to bring 0 dB. So as we proceed, did for lag compensator.
Other steps remain the same.
For lag compensator, what we did, we have to follow the same steps.
To second order. Yeah, they're not specific to second order. Only this formula for gain margin, this phase margin and gain crossover frequency, I wrote it because sometimes you are given a second order system in the exam, and you might be asked to find the gain crossover frequency or phase margin, and you are given omega n and zeta. So if that is the case, you can directly use this formula. Otherwise, you can always find the magnitude, put the value equal to 1, then get the gain crossover frequency. Using that, find the angle, and then get the phase margin. So there are many, many ways. But yeah, the standard one is if you have any order, use MATLAB.
Yes. And the transfer function we have taken for this example is there is no 0 in the original planned transfer function. So even if there is 0, it doesn't make any difference. So the steps are the same. Am I right, sir?
The steps are the same. Whatever we have to do, the steps are the same. But you just have to make sure from the Bode plot what are the requirements. So you should know, okay, my system is unstable. Or did you attend the last lecture where we designed this lead and lag compensator?
Last Sunday I attended, sir, root locus plot.
Yes. This in a similar way. We just have to understand. See, basically, this designing this lead or lag compensator is to find the transfer function, right? So we have to find the transfer function such that the specifications are met. So that's it. So we need to find Kc, alpha, or beta, and T. That's it. Anyone
Here
else?
you go with the maximum phi m and omega m maximum corresponding to that. No such step is followed in lag compensator design, sir.
Yes, that's true because they're different. So if you see when we studied this lead compensator in the previous lecture, what were we doing? We were providing the angle deficiency, right?
Okay, sir.
If you remember, we were providing the angle such that our specifications are met. Here, if you see the poles, if you see the polar plot of a lead compensator and a lag compensator as well, you should see the polar plot. So there you'll see it increases and reaches a maximum value and then decreases. Right. So that's why we get a maximum phase here in case of a lead compensator. Again, these details we have discussed in the previous lectures. You just revise or just go through the slides. There they will say why.
Okay.
Again,
you have uploaded it, sir. You have uploaded the video link. Have you?
Yes,
Okay,
yes. I
okay, I
will
will go through.
uploaded the previous one. Similarly, like I told in the last lecture, that why do we design a lead compensator, why lag compensator? In order for us to satisfy steady state requirements, we go for lead lag compensator. For transient, we use lead compensators and etc. So everything is discussed, as well as they're there in the NPTEL lectures.
Okay, okay, sir.
With this, I think you should be able to solve your assignments, because in
Okay, okay,
assignments
sir.
similar problems, and that it's more easy because you'll be using MATLAB.
Question, sir. One more question.
Yes, yes.
Sir, open loop transfer function is given, but sometimes it is asked, sir, whether the closed loop system is stable or unstable.
Fine. Yeah, no problem at all. Because when they're asking the closed loop system, it means there's unity feedback, right?
Yes, yes. Then we have to find closed loop transfer function.
Yes, the last step. See the last step
Yes.
here. So last step, I'm finding the open loop. So here I'm finding the open loop. This is my open loop transfer function. See, this is my OLTF again. But here you will find the closed loop. It's nothing. Just you have to close the loop. In MATLAB itself, you'll do that. Just feedback, do unity feedback, and find. And I think this specifications will be made for closed loop system as well. If they are made for open loop system, but again, you need to check.
Okay.
Right? Just do the unity feedback. That's it.
Okay, sir. Thank you.
No need for 1 plus GH of S, sir.
No
No need
need.
for
No.
1.
Why would you do that? Because you're allowed to use MATLAB. That will actually be doing that, but you will just write feedback gc of s and g of s using that command. You'll get the specifications. Otherwise, you have to do that 1 plus. So this gc of s, g of s, it will be g of s, new g of s. Then your closed loop system will be relation g dash of s, g dash of s, 1 plus g dash of s. So it will be like this.
So this is our now new problem for the transfer function. For this one we have to design it.
Yeah,
If
no,
it is
it's like you
for
just need
closed
to
loop.
check. You have already designed. So you need to check whether this is satisfying for this as well. Whatever you have designed. If it is not satisfied, then again you need to vary. Like in the last lecture, we saw how this whole zero locations they impact the specifications. For example, we took two cases in case of a lead compensator, where we saw in one case the specifications were far away, but in other case where there was a pole zero cancellation, the specifications, the results were very close. So here as well, if you are not fulfilling, either you have done incorrectly, or you need to modify the pole zero locations based on what you have obtained. So it's like there is always a possibility of hit and try. But at this level, I don't think that is needed. So with this, I think you should be able to solve all your assignment questions. Is that clear? So if nobody has any questions, then we may stop this meeting here. Okay. Thank you so much for attending.
Okay, sir. Thank you.